So this is the last topic in our gas laws chapter, and I want to revisit the definition of laws and theories before we go through this kinetic molecular theory of gases. If you remember, laws, by definition, enable us to predict what will happen under a given set of conditions. So gas laws are useful when we wish to predict the behavior of gases under varying conditions, but they do not explain the behavior of those gases. Theories, on the other hand, explain why we observe the predicted behaviors. For example, Avogadro's law describes the observed experimental relationship between the number of moles of a gas and the volume of that gas. However, it does not explain why 1 mole of the relatively small helium atoms at STP has the same volume as 1 mole of a much larger molecule, such as sulfur hexafluoride, at the same temperature and pressure. So Ludwig Boltzmann and James Maxwell proposed the kinetic molecular theory to explain the observed physical properties of gases in terms of molecular motion, which we know is a form of energy called kinetic energy. So the first statement in kinetic molecular theory basically defines a gas. And the gas is defined as gas molecules being hard spheres without internal structure. These molecules are separated from each other by distances that are greater than their own dimensions, and the molecules are points. They have mass, but essentially zero volume. It also states that gas molecules are in continuous motion, and because of that, they collide with one another and the walls of their container, and these collisions result in the pressure of the gas. So the collisions are responsible for the pressure of the gas. Also, as these molecules collide, energy is transferred between them. So these collisions are what we would call elastic. Third statement, gas molecules do not interact electrostatically. They are neither attracted or repulsed by one another. So there's no attraction or repulsion among those molecules. And the fourth statement is the average kinetic energy of the gaseous molecules is proportional, to the temperature of the gas in kelvins. Remember, gas laws are based on temperature in kelvins. The identity of the gas is not relevant. Two gases at the same temperature will have the same average kinetic energy. And there is an equation that is used to calculate that average kinetic energy. You're not going to be responsible for this equation, but I want you to understand what the variables are in the equation. So Ke is the kinetic energy. The line above it tells me that's the average. M is the mass of the molecule, and U equals the speed of the molecule. U squared, with the line above it, is the mean square speed, or the average of the speeds, or the average velocity of all the molecules in the sample. So we're going to look at two phenomenon, diffusion and effusion, and this is Graham's law of diffusion. And it basically states that at constant temperature and pressure, the rates of diffusion for gases are inversely proportional to the square roots of their molar masses, as shown in that equation, R1 over R2, which are the diffusion rates of gas 1 and gas 2, and the molar masses of gas 1 and gas 2. And we will be working with the equations for both diffusion and effusion. Effusion is the process of moving from a region of high pressure into a region of lower pressure. So the gas molecules move just like heat is transferred from a high region to a low region. And Graham recognized that the rate of effusion of a gas is related to its molar mass. So this is Graham's law of effusion, where the rates of effusion are inversely proportional to the square root of the molar masses. And these are typically expressed in time, units of time. So you'll see R1 over R2, which are rates, is equivalent to T2 over T1 in units of time. So diffusion versus effusion. Diffusion over here and effusion on this side. Diffusion is a time-dependent process that results in the gradual mixing of molecules of one gas with molecules of another by virtue of their kinetic energies. So this is gradual mixing. Of one gas with another. Over a period of time. Based on kinetic energy. And R1 over R2 equals the square root of molar mass of gas 2 divided by the molar mass of gas 1. You might also see U used to represent R, or rate, but these are rates. Effusion, also time dependent, that results from gaseous molecules moving from a region of high pressure to a region of low pressure. And as we saw on the prior slide, T2 over T1 equals the molar mass of gas 2, the square root of the molar mass of gas 2 divided by the molar mass of gas 1. So now let's try an example of each of these problems. And we're going to do a diffusion problem first. And we are told that the diffusion rate of H2 gas is 8 times that of gas X. And we're asked to calculate the molar mass of gas X. Okay. The molar mass of H2 is 2.02 grams per mole, rounded to 2 decimal places. And it can make our life simpler if we simplify our equation before we plug in our variables. And so we have R1 over R2, the rates, and we'll define rates for R1 and R2 momentarily. Again, equals the square root, gas 1. So if we square both sides of this equation, we can eliminate the square root. So R1 squared divided by R2 squared equals the molar mass of gas 2 divided by the molar mass of gas 1. Okay? Now, we're going to solve for, I'm going to define H2 as gas 1. So when we rearrange this equation, it's a bit easier to manage. So, which rate are we going to assign to H2? We're told that the molar mass of, what did I just say? Sorry about that. The diffusion rate of hydrogen gas is 8 times that of gas X. So that means that we want okay, I'm going to pause this for a second. Okay, let me start that over. We are going to assign gas 1 to be H2. I just lost my train of thought there for a minute. So that means that the rate for H2 equals 8, and the rate for X will equal 1. So when we put our variables into our equation, try to preserve some space here, we have 8 squared over 1 squared equals X, so this is molar mass of gas 2 over 2.02 grams per mole. Now we just rearrange and solve for X, which equals the molar mass of our second gas, and that is 129 grams per mole. Effusion example, and I'll have more practice problems for you on D2L. We are told the effusion time of gas X is 6 seconds. the effusion time for the same amount of hydrogen gas is 1 second. Calculate the molar mass of gas X. So because it's effusion and we're given our variables in time or seconds, we have T2 over T1 equals the square root molar mass 2 divided by molar mass 1. Okay, so same process, simplify this by squaring both sides, and we'll get T2 squared over T1 squared equals the molar mass of 2 over the molar mass of 1. And again, we will assign gas 1 to be the hydrogen gas. Okay, so gas 1 equals H2. It diffuses in 1 second, and again it has a molar mass of 2.02. So we have 6 squared over 1 squared equals molar mass of gas 2 over 2.02 grams per mole. And when we solve for molar mass of gas 2, we get 72.7 grams per mole. And finally, we've been treating all gases as ideal gases, and under typical atmospheric pressures and temperatures, most gases do behave as ideal gases. However, what happens when we begin to compress gases into increasingly small volumes or cool them down to extremely low temperatures? And when we do that, gas properties deviate from ideal behavior. So the van der Waals equation was developed in order to correct for pressure and volume. A and B are van der Waals constants, and their values have been determined experimentally for each gas. And A and B increase with increasing molar mass and the number of atoms in the molecule. B is related or is a correction for molar volume or molecular volume, and A over V2 corrects volume 2 squared, corrects for attractive forces, because when you compress those gas molecules closer and closer together, then they are forced to interact with one another. Okay, so we will not deal with this equation. You should understand the what the A and B corrections are, and that's about all you need to know here. I think there we go. So V minus N times B corrects for volume, and P plus A N squared over V squared will correct for those attractive forces. And that wraps up our gas law content. We'll have one more chapter to cover before the semester ends. And again, I'll have some practice problems for you on D2L.